All right, now we're done with the review stuff. So now we're going to get into the actual thermo part of the course. Okay, so we're going to start with looking at work again. We talked about work. We reviewed it in terms of the mechanical sense of work. So that's what we looked at just a second ago. So the equation we looked at before was work equals the integral as we go from position 1 to position 2 of a force dotted with ds, where s would be displacement. Now remember, with work, you've got to have a displacement in the same direction as your force, okay? Because you got to be able to take this dot product, and like I said before, dot product is for parallel components. So you got to have a force going in the direction as your displacement. Okay, so this is our equation we looked at before. Now in thermodynamics, we've got other things to consider besides just mechanics. All right, we need a broader interpretation of work. So the way that we're going to describe work in here is a little different. The way I want you to think about it is I want you to consider having a weight of some kind. All right. Now, work is going to be done if your system has the ability to raise the weight. Okay? So if you can move that weight somehow, you've got work being done. All right, so work is going to be a means for transferring energy. That's what we are talking about when we're talking about the thermodynamic kind of work. All right, it's going to be a means to transfer energy. Now we're going to have a sign convention for work. This is going to be something you're going to need the rest of the course. So you might want to highlight it. So if work, which is W, is greater than 0, we're going to say that work is done by the system. Okay, so it's done by the system. This word by here is the important word. Okay, and you'll see why when we get to the examples. Now if work is negative, so if it's less than 0, then we say work is done on the system. Okay, so that right there is going to be important. Now the difference between these two, let's think about the work being done on the system. When we say work is being done on the system, that's going to mean there's some sort of external energy that is being supplied to our system to make that work happen. Okay, and you'll see when we get to the examples. And then when we say work is done by the system, that means the system itself can generate work. It doesn't need the external sources to generate the work. Okay, so I know it's kind of confusing when you first hear about it, but if you wait to get to the examples, it becomes a lot clearer. All right, but for now, just remember these sign conventions. These are going to be important. Now, we also show directions of work with arrows on our figures. So if I was to draw a box and this represented a system, if I draw an arrow going into that box with a W by it, that means work is less than 0. So this is showing me I've got an external source of work here. So work's going to be less than 0. Now if it's drawn the other way, where the arrow is pointing out, that means work is greater than 0. So this is meaning work is done by the system. All right, so we can send energy out. Think about it that way. Okay. Now power is directly related to work. So our symbol for power is going to be the W with the dot there. And what it is it's the rate of energy transfer by work. Okay, and our equation is going to be W dot equals F dotted with V. So this is the force, dot product, and then here we've got velocity. Okay, and if you haven't seen this dot notation, that just is the time rate of change, so that's just like the first derivative. So don't get confused by the dot. just indicates the derivative. Okay, now our units for power, we're going to have joules per second or a watt. And a watt is denoted with a capital W for the unit. Those are the SI units. In English system, we're going to have foot-pound force per second, BTU per hour. BTU stands for British Thermal Unit. And then finally, horsepower. Okay. So now let's get into an application of work. So this is going to be over expansion compression work. And what we're going to do for this is we're going to consider a closed system. Remember, closed meant that there was no, let's try to zoom in again. There we go. That means there's no mass transfer across the boundary. All right, so the mass you start with is the mass you end up with. Okay, so we've got a closed system with a piston cylinder assembly. One end is going to be filled with a gas, and then that gas is going to expand. So that's what we're going to start with. So let's draw a picture here. All right, so there's my cylinder, and I'm going to have a piston in here like that, and this is where it's going to start out. So let's just call this X1. So that's my initial position. I've got a gas in here, and it keeps, well, stay focused, guys. There we go. So I've got a gas in here like that. Okay, now this gas we're going to say is going to expand. Now as this gas expands, what's going to happen? The pressure from the gas is going to push on this piston, and it's going to move the piston to the right. Okay. Now what happens with that, let's think about it. We started out with this volume, V1. Now if the piston moves to the right, and let's say it moves over to here, all right, so this will be our second location. Now we've got a much larger volume, right? Because now we have all of this plus all of this. Okay, so now we've got an expanded volume, and all of that was caused by this force right here. And this force was caused by the pressure. All right, and remember, force is pressure times area. So this will be our, it's actually a normal force, let's put that. So normal force due to expansion of gas. All right, and remember P is the pressure on the piston face. And A would be the area of that piston face that's in contact with the gas. Okay, so now we've got that. Now what we want to do, since we move this piston, all right, think about this as being a weight. We were able to move that weight, right? We moved it. So we've got work being done. So work is force times distance. Okay, now the equation we're going to use is we're going to have delta work equals P times A, so this is pressure times area, so this is force, times dx. So this will be distance. Okay. Now we have that. Now if you look at this equation, we've got an area times dx. So let's look at that product. Now if we just think about the units, area units will be meters squared if we're in the SI system. dx, remember x is a distance, this is just a change in distance. So units for that would be meters. Now if you put those together and you multiply them, what do you get? Yep, you get cubic meters. Now what units go with cubic meters? What is that? That's volume, right? So that means we can write A dx as dV, where V is volume. All right. So now if we do that, we can say that we've got pressure times dV. And this little delta here, this is just another symbol for change. So we've got change on both sides. We've got delta and then we've got this d here. So that means we could integrate both sides. And then what we're left with is work equals the integral from volume 1 to volume 2 of the pressure times the change in volume. Okay, so this is going to be the work due to volume change. Okay, and we are going to use this a lot. Okay, and it's actually a pretty simple equation, and I'll show you how to use it in the next example. So I'll see you then.